We're going to talk about solid state resistance spot welding method. My name is Kelvin Shih. I'm a retired professor of electrical engineering from Lawrence Tech University, Southfield, Michigan. John Pippin Jr. is the general manager of Milco Manufacturing Company in Warren, Michigan. The resistance spot welding has been used to join a car body for almost 100 years now. Since the beginning, expulsion is always accompanied each weld. Expulsion often produces undesirable features in a spot weld. It is frequently linked to excessive surface indentation, electrical wear, sheet distortion or separation, and volume defect formation, or we call it cavity. This lack of progress in such an important manufacturing process can be directly contributed to the mistaken belief that you have to melt the metal in order to weld. In 1995, the Intelligent Resistant Welding Consortium was organized to improve the quality and the consistency of the weld and eliminates expulsion welds. The consortium also like to develop a new way to inspect each weld in real time. After $13 million and 5 years of time, this effort fails. This is the project brief of the Intelligent Resistant Welding Consortium, and this project lasted 5 years and total funding is about $13 million. Out of that $13 million, about $6.4 million is from the federal government, the National Institute of Standards and Technology. After 2000, there's very little was accomplished in developing a new weld controller, and between 2003 and 2006, there are two of the big three automakers had given a weld control company $2 million approximately, and after 3 years the money runs out, nothing was accomplished also. This diagram, weld load diagram, consists of x-axis is the current, the y-axis is the weld time. And this weld loop have two curves. On the left hand side is a blue curve. The right hand side is a red curve. The blue curves separate the acceptable weld from undersized weld or no weld. The red curve separates the acceptable weld from expulsion welds. And the whole thing is experimentally found, is done under a fixed force. I always wonder what those two curves are. And in a book called Resistant Welding Fundamentals and Applications, on page 197, it says at a fixed force, the current representing the minimum and the maximum current that can produce acceptable weld. And the minimum current is separating acceptable weld from undersized weld. The red line, maximum current, separates expulsion weld from acceptable weld. If this is the case, those two curves is no longer a curve. they are become two vertical straight line. And since that is not the case, so this theory about minimum and maximum current is actually not correct. If we add more description to these two curves, on the left hand side of the right curve, since the other side is an expulsion wall, so the left hand side has to be non-expulsion wall. Since the left hand side is an acceptable wall, so the right hand side has to be an unacceptable wall. We can add two more lines of description on this weld load. The expulsion wall is a fusion wall, so we add fusion wall right underneath. The left hand side of the red line, if the right hand side is fusion wall, the left hand side has to be solid state wall. Let me add two more descriptions to this curve. Since fusion wall is a melted wall, so I add melted wall below the fusion wall. Since solid state wall is not a melted wall, so add not melted wall below the solid state wall. As soon as we see that, we can tell the red curve is actually the melting temperature line. In the case of steel, it's 1500 degrees C. And because of this, we can say the blue line, which separates the undersized wall from not melted wall, is the coalescent temperature line. Coalescent temperature normally is between 50% to 90% of the melting temperature. In the case of steel, that is 750 degrees C to about 1350 degrees C. By now we know all the accepting walls, they are solid state walls. All the expulsion wall is not unacceptable, is unacceptable wall. From the previous slides, we found out that the weld load curves, they're not a time and current domain curves. They are actually a temperature domain curves. From that, we can also write an equation, simple equation, to define a good weld without expulsion. Let's say the T center, the temperature at the center of the wall. T edge is the temperature of the edge of the wall. T coalescent is the coalescent temperature of the metal, and the T melting is the melting temperature of the metal. A good acceptable wall without expulsion can be defined by the following equation. The T edge equal to T coalescent, and the T center has to be larger than the T edge, which is always the case. And this defines a good weld. And if the T center is smaller than the T melting, then this is not only a good weld, it is also a non-expulsion weld. This is a plant near Cairo, Egypt.
Nice.
هل بص بقى ما انا المفروض بقى عايزين الثابت. بص الثابت فين؟ حاجه كله ايه بقى؟ You would have to change
You want the front one to move, not the back one.
they want to switch the jaw around.
They, well,
Lower on the top.
they want the gun to be rotated.
It's tight.
Yeah.
مسافه بتيجي واحد عايز السن من ناحيه الثانيه. هنا في مشكله برضه. خلي عليها جايه هشوف.
A pinch gun. A pinch gun. Right? Straight action.
When you heat up a piece of metal too hot until it reaches its melting temperature, then this metal will change from solid to liquid. And there's some of them melting temperature is worthwhile for us to remember. Steel is 1500 C, and for copper is 1083, for aluminum is 660, zinc is 420, and the one more thing important, that is the boiling temperature of zinc is 918 degrees C. Solid state welding and the fusion welding. Fusion welding is a welding process that relies upon melting to join materials of similar compositions and the melting points. Solid state welding with similar material is caused by solid state diffusion. Due to this, solid state welds is often stronger than the individual metal. The temperature required to weld solid state weld is typically 50 to 90% of that melting temperature. Because of this, solid state low temperature weld usually only uses a fraction of the energy of an expulsion weld. When welding solid state weld, the metal may take on a glossy or wet appearance at lower temperature. Solid state welds does not produce HAZ, or heat affected zone. Why we weld unacceptable expulsion welds? The main reason that we weld so many expulsion welds is that most of the people still believe that you have to melt the metal in order to weld. So they will program the weld schedule very close to the melting temperature of the metal. A good example is in the Rex Ross U/I regulator PSQ 6000 manual, page 17. It actually recommends you to push it all the way to the expulsion, then back it off one step. Number 3, the cause of expulsion are both technical and human related. In the latter case, expulsion is often used as a visual indicator of correct welding process in steel welding. That's from the paper by Dr. Zhang, Expulsion and its influence on weld quality. Number 4 is the phobia of making undersized weld or no weld drives people to make expulsion weld. Last one, the weld controller simply does not know how to weld a solid state weld consistently. Underneath the melting temperature part of the table, it says it takes a quantified amount of energy to melt a volume of metal that will produce a weld nugget. So WTC still believe in melting in order to weld. This is also a slide I downloaded from WTC website, and the title says it all. Expulsion, terrible but better than missing weld. I found this slide interesting because it says the weld lobe only 200 to 300 amps wide. From my experiment, the weld lobe is over 3,000 amps wide.
Okay, start.
Okay. You measure the whole thing 6.8?
Yep.
Okay. So did you have to peel it, right?
Yep, we have to do this coupon first.
So how many points on the coupon?
3.
3.
Okay. Peel it.
And you know it's a good weld when it's tearing away the base material with it, instead of splitting the actual weld. First weld, 6.01. Second weld, 5.88. And your third weld, 6.03. So you're right where you want to be.
We have welded several welds on a large sheet of metal, which is zinc-coated steel, and then the coupon, which is also zinc-coated steel, and there's no smoke coming out of it. This means all welds are formed below the 918 degrees C, which is the boiling point temperature of zinc, and all of them exceeded the minimum weld size of 3.15, and we are welding, in this case, low temperature weld, so the nugget size should be 1 millimeter smaller than the weld cap size. Weld cap is 6.8 millimeter, so we're expecting 5.8 millimeter. The result is 6.03, 5.88, and 6.01. So this proof, without the shadow of the doubt, you can weld without melting any metal. Do do you have to melt in order to weld? Most of the scholars say yes. In their paper, they sometimes talk about solidification of liquid nugget, melting, and the liquid nugget again, molten nugget, and molten metal. Okay, and most of them think about there is a weld schedule you can find that weld fusion welds, but there is no expulsion. And later on, I can prove that is simply not the case. This is a picture of simulating a weld, a spot weld. You notice the center of the weld is this purple color. And according to this picture, the purple means molten. This part of it is the video that Swantech showing on their website. Did you notice the center of the wall turning purple? The purple means molten metal. So they are simulating a fusion weld as well. Unfortunately, as soon as the center turns purple, you will have expulsion, and this is unavoidable, and they just ignore it. Do you notice that this is the simulation of aluminum welded to steel? At the fitting surface, you are both at the 1500 degrees C and the 660 degrees C. This simply doesn't work. This cannot work in fusion welding at all. So it is a solid state welding. This is basically the Bosch Rexroth ultrasonic adaptive welding. There are two sensors. One of the transmitter, the second one is a receiver, ultrasonic receiver. The frequency they're using for this ultrasonic is about 2 megahertz. And you have to add about 2 or 3 boxes in order to sense the transmissivity of the ultrasound. And from that, you determine when this thing start melting. And then you can stop the weld just while it's about to melt. This is the transmission curve versus the time. And if you notice, at the very short time right after the weld started, they claim it started melting and melting and again melting and melting until this whole thing is stopped. The weld is terminated. In real life, melting only happened at 1500 degrees C for steel. And as soon as you melt any amount of metal, the expulsion happens. And simply, this idea you can keep on melting from the very beginning until the end is incorrect. This is the curves from the PSQ 6000 U/I controller, and the red one is the current, the blue one is the voltage, and the green one is the resistance, which was calculated from the current and the voltage. And the interesting thing is, okay, they recorded this thing and displayed on the tubes, and later on they declared this thing is useless. This page is from Rexroth's PSQ 6000 controller, page 17. The top part of it basically asks you to weld until expulsion occurs, then back down one step. The middle part, the quality of the weld cannot be determined by an interpretation of the curve characteristics. Controlling the curve characteristic must be limited to the following assessment: resistance characteristic and so on. The last part of it, expulsion can also be detected by a sudden downward slope of the resistance characteristics, which we all know that. The last part, the cap wear condition, which they mean the dressing of the weld cap, should be between 10 and 100 welds. If I can dress a cap every 10 welds to 100 welds, I really don't need this thing to control. All I do is welding by constant current. On page 24 of the same controller manual, it says monitoring will turn the monitor function of the U/I on and off, referred to certain section. Then talk about expulsion. Detection of expulsion has been assigned to a default value, should not be changed unless specifically requested. Then they have a weld counter to count how many welds from the reset. Then they have an expulsion counter, okay, which means this weld controller really cannot control the expulsion. They're mainly counting the expulsion, the number of expulsion among the total welds. Blacksmiths usually use the color of the steel to tell whether it's hot enough to start working on the steel. And the color, most important one, is about the cherry color, which is about 745. Then salmon is about 845, and lemon is about 1000, and white is about 1205. Even this thing become white, is still about 300 degrees C below the melting point. There is a flare device, and only costs $60, and that can measure temperature of the steel from 0 to 2000 degrees K, or from 0 to 1727 degrees C. Although the precise details are not known about the actual method used by the early blacksmiths and the craftsmen, it is evident that solid-state welding has been used for more than 1,000 years. For instance, the famous ancient Japanese and Damascus swords were made by hot forming a piece of high carbon iron into thin strips. Each strip was then folded into two halves lengthwise, which were themselves again welded to each other by hammering at high temperature. This process was repeated tens of times in order to improve the strength and toughness of swords. This is from Diffusion Bonding by Amir Shahzadi. This is a picture of a craftsman trying to make a katana sword. And you can compare the temperature of the piece on the anvil to the right hand side, the color chart. And I would say is about the salmon color to maybe the orange, which is about 845 to 940 range. And this piece is not melted at all. And so this process has to be a solid state process. Even about 90% of all professors believe that resistance spot welding is a fusion process, but there are two professors wrote a book. The book is called Manufacturing Engineering and Technology. And these two guys' name is Kelvin and Schmidt. They, on chapter 31 of that book, they listed all the solid state welding processes. They included the seam welding, resistance spot welding, and stud welding, projection welding. They are all solid state welding process. Solid state welding processes. Number one, joining takes place without fusion at the interface. Number two, no liquid or molten phase is present at the joint. Number three, two surfaces brought together under pressure for stronger bond, both surfaces must be clean. Another way to weld two pieces together is called solid state bonding. What happens is that diffusion transfers the atoms across an interface. When this thing can be facilitated by heat, and we can generate heat either by friction, by electrical resistance, or by induction. Pressure. The higher the pressure, the stronger the interface. May combine pressure and the resistance heating. That is giving us the resistance welding. One of the welding methods is called roll bonding or roll welding or cladding. You basically take two sheets of metal and put a different sheet of metal in the middle, and then you use a heated roller to heat this thing up and apply pressure at the same time. Now all of a sudden all three sheets become one.
A quality pot and pan has the ability to heat uniformly throughout so that food cooks evenly. Copper is by far the best heat conductor, but copper cookware is very expensive. Aluminum conducts heat well but isn't durable, so many cooks use stainless steel cookware that contains aluminum. This high-end line of stainless steel cookware has an aluminum core running throughout. Production begins with two stainless steel sheets. Using a spot welder, workers tack them together along one side. Then they lay the connected sheets onto an assembly fixture. A vacuum arm pulls up the top sheet, and they insert an aluminum sheet in between. This metal sandwich goes onto a conveyor that takes it on a 10-minute ride through an oven. The heat, 700 degrees Fahrenheit, softens the metal. This preps them for the bonding and shaping operations to come. From the oven, the metals enter the first mill, which uses electric current to heat and bond the 3 layers into one. Now it's into a second rolling mill. This one strengthens the bond. That steam you see is the water-soluble lubricant evaporating against the hot metal. Now the bonded metal travels to a second oven for reheating. This further strengthens the bond. From there, it's into a 110-ton press. It forces down a die to cut out the starting shape of the piece of cookware they're making.
Seam welding is also one of the solid-state welding method, and you use 2 copper wheels, and the sheet metal is in between the 2 wheels. The wheels both provide the current as well as the pressure. Swan-Tech simulated this seam welding as a fusion welding process, and that's why you can see the purple color, which means molten. This is to weld a muffler. You notice there is no smoke, no nothing. So the welding temperature is below the 918 degrees C evaporation temperature of the zinc coating. Those gas come out of there. They are the vaporized zinc. The zinc boiling point is 918 degrees C. So the weld is performed above 918 degrees C. In this book, resistance spot welding is also considered to be a solid-state welding process. Swan-Tech did a simulation, but they treated the resistance spot welding as a fusion welding process. You can see the center part of this thing is actually turned purple. Purple in this case means molten. Molten means this is a fusion weld. You melted the metal in order to weld. There is a company called Sunstone Engineering in Arizona, and they make the micro welder, and they routinely welding different metals together using resistive welding method. In this book, the projection wall and the cross wall is also considered as a solid state wall, and this is very easy to prove because we can see the nugget from the outside. Again, Swan-Tak simulation consider the projection wall as a form of fusion wall. You can see the purple color appears again and again, and in real life that's actually not happening. This is the picture of cross wall. I want to bring to your attention is the color temperature of the steel sitting at the right hand side. This is the picture of a projection wall, and please remember the right hand side, the color temperature of the steel. Both the cross welding and the projection welding, when you compare the weld itself, the weld nugget itself, to the color chart, it's about 900 to 1000 degrees C, which is 500 to 600 degrees C below the melting point of 1500 degrees C. Because that, those welds has to be solid state wall. It cannot be fusion wall. And the differences between a spot welding and the projection welding is that you can see the projection welding, the nugget, is exposed to you for you to see. And so we can tell from the color of it what temperature it is. If the projection welding is a solid state welding, for the same token, the resistance spot welding should also be solid state welding. Yeah, this is a picture of a piece of aluminum welded to a piece of titanium. The differences of their melting point is something like 1100 degrees C. And yet, by using solid state welding techniques, you can weld them together very good. This is an experiment run on August 7, 2014. The weld time is 170 milliseconds. Diameter of the weld cap is 6.5 millimeter measured. I started out with 9.2 kiloampere of current, and my weld average diameter is smaller than 5 millimeter. So I said, this is not good, okay? Then I started 9.4. I started getting welds which is over 5 millimeter, which is good. All the way to about 12.0 kiloampere. You see this point, this nugget is about the same size as the weld cap diameter. Okay. Next one is 12.5 kiloampere. All of a sudden, I have one solid state weld, 2 expulsion weld. The average is 6.46. Okay. This is very interesting because the professors always assuming there is a weld schedule that both give you fusion welding and yet no expulsion. That if there is such a weld schedule, that weld schedule has to be between this point and this point, right in the middle. Yeah? Since the whole thing, this coupon number 10, is welded with the same schedule, 12.5 kiloampere, 170 milliseconds. So there is no possibility there is something between a weld schedule between this one and this one that can give you fusion but non-expulsion weld. Okay? Let's remember this is at the 377 ampere per square millimeter, and the first group of good weld is 283. So I take 283 plus 377, divide by 2, that gave me about 330 amperes per square millimeter, which is about 11 kiloampere. Yeah. And at this 6.5 millimeter size of cap. And this is important because we should choose the current based on this current density, not just the current. Okay, we pick the current density like 330, then we multiply by the area of this cap, then we can get the right current. And another way to demonstrate there's no way you can weld a non-expulsion fusion weld is to use a Venn diagram. On one side of the Venn diagram we have acceptable weld, non-expulsion weld, solid state weld, not melted weld. On the other side we have non-acceptable weld, expulsion weld, fusion weld, and the melted weld. There's no way there's an area can occupy both sides of this circle. So the professors, they assume you can weld a fusion weld without expulsion. I think that dream will not happen. We can use the data we did in experimental 1 to plot it on a weld load. It will look like this picture, and there's one undersized weld which is less than 5 millimeter, then the rest is all solid state weld, good weld. And the number 10 coupon is the yellow one sitting right on the edge of melting point melting temperature. And right hand side of the red curve, we have two expulsion wells. When we understand expulsion well is not repeatable, is not controllable, we then can start welding more and more the solid state weld. This is experiment 2. It was performed May 19, 2014. This time the current is kept at about 10.1 kiloampere. The diameter of the caps is still 6.5 millimeter, and the current density is about 304 amps per millimeter. And for the first one that get a good size nugget is 170 milliseconds. We got an average of 5.64, which is approximately 1 millimeter less than the diameter of the electrodes. And this thing go on for 9 coupons, and from 170 to 425 we are getting more or less identical size nugget. From 9 to 10 we only increased 25 milliseconds, and all of a sudden the nugget size jumped from 5.7 to 6.5. Then from coupon 10 to coupon 16, all the nugget size are equal to the weld cap diameter. Then from from 17 to 35, all the nugget size are slightly larger than the weld cap size, so it getting to the 7 point something range. And at coupon 35, we are still not making expulsion weld. Because the last experiment, we can clearly divide the weld lobe into 3. Low temperature, medium temperature, and high temperature. When I weld my weld, I always put the weld schedule near the line between the low temperature and medium temperature weld. And while other people, when they weld, they usually put their schedule right in the expulsion weld region, or right on the 1500 degrees C melting point line, or just slightly below that line. This slide, I choose the first 10 coupons data to plot it on this weld lobe. You can see the whole thing divided into 3 parts. The 10 of them coupons I choose. The 0.450 is the last one that fell right on the line between the low temperature and medium temperature range. From the data we collected, we can build a model of this weld, and I draw up a picture of, I call it target ring. The inside of the target ring area, the center of the nugget, is always the hottest, and that I call it the center temperature. Then at the first target, the target is called a target ring because we wanted to weld something close to that size. And the target ring diameter is generally 1 millimeter smaller than the electrode. And the outside, the green area, is the electrode diameter. And if we welded the target ring, round target ring, or we are talking about a low temperature weld. If you weld it in the electrode diameter, that is a medium temperature weld. When you welding solid state weld, there's only two sizes I like to choose. A low temperature weld, if you have a 6.5 millimeter cap, you will be welding 5.5. But if you have a 7.5 diameter, electrode diameter, you will weld 6.5. If you have a electrode which is 8.5, you will weld 7.5. Medium temperature, if you have a 6.5 cap, you will weld 6.5 nugget. If you have 7.5 millimeter cap, you will weld 7.5 nugget. This picture is a expulsion weld. You can tell from the cavity in the middle and the deep indentation and the Shih separation. This is the picture of a high temperature weld. You still can see very deep indentation, and although there is no cavity there, you can clearly see the HAZ and the border of the HAZ. And the nugget itself, because it heat up to high temperature, then recrystallize. So you can see a lot of dendrite. This is a picture of the dendrite, except it's amplified a little bit closer. And we can see the FZ, which is the fusion zone. HAZ is the heat affected zone. And you see the corner, there's 20 micrometer how wide it is. This is a low temperature solid state weld. You can clearly see the interface, there's no line. And both sides, the metal look the same. And there are no, what they call the dendrite, there's no heat affected zone in a low temperature weld. According to the Handbook of Structural Welding by John Lancaster, page 83, it says ferrite steel may be affected in two ways. First, there may be embrittlement due to passing through the overheating temperature range. Secondly, the transformation products associated with the coarse grain austenite may have inferior property. Overheating may occur if steel is heated to a temperature above 1200 degrees C and then cooled at a rate between 10 to 200 degrees C per minute. It is manifested by matte facets in the fracture surface and the reduction in ductility impact strength and fracture toughness. Burning is associated with heating at temperature of 1400 degrees C and over, and this results in severe loss of toughness and a completely intergranular fracture. If you're welding too many expulsion weld, the surface of the copper become very hot, and the heat will make the surface very malleable with high pressure, and sometimes the weld caps start mushrooming, which means its surface area become very much large. Too much expulsion weld in some cases can completely destroy the weld caps. On November 2013, RWMA, the question and answer part of it, one of the engineer is writing the magazine for help, and the author Donald Matz answer, okay, and the plea for help sounded like this: we are resisting spot welding on galvanized coated parts and experiencing what we consider to be a short electrical life. We start each production run with welds that barely meet the size requirements, but finish with expulsion so severe we end up destroying the electrical phase. We are hesitant to change the weld schedule due to a small initial weld size, and have, instead of focusing on current stepper, to little effect. The water flow, electrical cap size, weld force, secondary current, and the weld time are all in line with the RWMA guidelines. Any ideas will be appreciated. And this describes the controller completely lost control of the welds. And to solve this problem, the only way we can is to eliminate all expulsion weld, not just a certain percentage of it. Once we can do that, there's hope to really regain the control over the welds. Mr. Donald Matz, I have the pleasure to meet him once for a couple hours, and he is absolutely an expert in this field, and I have learned a lot from him that day. Thank you, Mr. Don Matz. Because the modern weld controller are so poorly designed, and it really cannot eliminate all the expulsion welds. So under this kind of condition, Mr. Don Matz recommended a way which is, I think, is the only way it can work under the circumstances. That is, you keep the current constant, and you dress it often, okay, and dress early. This way you can maintain the current density without trying to use the stepper. Current stepper is one of the worst things ever invented, because it doesn't work, and it actually created a lot more expulsion weld because of the use of stepper. This is our expulsion-free weld controller / monitoring device. This system is designed to well, solid state well. It has a building model of a solid state well growth algorithm, and the control consists of 5 switches, so it is very easy to program. And the display, there's 3 displays. One of them is LED, white color, red color, and green color, to tell you whether you have a well or not by the white color LED. Green color LED tells you that you have made a good well. Red LED tells you you made a suspicious well. And this device, the right hand side top is a 3-digit LED display that give you the time, well time reading. The bottom is a 3-digit display that in manual mode it give you the current setting. In auto mode it actually tells you exactly what the expected diameter of the next well. And using this is extremely easy. Expulsion free well controller / monitor. Number 1, expulsion free well controller monitor uses an accurate model of the nugget to monitor the temperature of the well. Number 2, when the set temperature is reached, the well is terminated. Number 3, because the nugget never reaches the melting temperature, no expulsion well can be produced. Number 4, the controller set the current based on the temperature and do not use current stepper. Number 5, the solid state well uses less than half the energy than expulsion well. Number 6, the quality of the solid state well is better than the expulsion well. We have talked about that before. Number 7, when the well cap changes, this controller changes the nugget diameter. Number 8, this controller can tell you whether a well is in progress or not by using a group of 12 white LEDs. This actually is used to replace the people that trying to use the expulsion as a well indicator, visual indicator. After the well, a group of green LED tells you it is a good well. If the red LEDs turns on after the well, it is indicates it is an open loop well. Number 11, this controller can predict the well size before the start of a well. When you wanted to make a manual well, the auto manual switch position will be manual, capture, and the store position switch position will be in capture. The top 3 switches is used to adjust the time and the current, and the light at the top doesn't mean anything at present time. When you're welding in auto mode, the capture and store switch will be in the store position and the manual auto switch will be in the auto position. The weld time is still the same or 10% larger than your initial setting. And the bottom line says current in kiloampere. Now that is actually reading the diameter, predicting the diameter of the next well. And the green light is after the well. If the green light turns on, you made a good well. in auto mode, every time you trigger, it'll go through red, white, and green. All the previous experiments are done in manual mode, and now we're going to try the auto mode welding. And so-called adaptive welding, it is all done in auto mode. And what we do is this: we made a couple coupons in manual mode and peel them, take the average, and then set the whole thing up, flip the switch to auto and to store, and then adjust the pot in the back of this to the average nugget size. Then all of a sudden we're ready to weld auto mode. This is a repeatability test or consistency test. The welder is programmed at 12.0 kiloampere, 350 milliseconds, with a 6.4 millimeter weld cap. And this thing is in the medium temperature welds. So we expect the predicted and the measured nugget close to 6.40 millimeter. This is from number 1 to number 33. Okay, and number 34 to number 66 is listed here. The blue color one is the predicted nugget diameter, and the measure is over here. Did it 102 welds because 100 just don't divide it by 3. So we took all 102 welds, average it. The predicted average is 6.39 millimeter, and the predicted measured nugget diameter is 6.39 as well. Compare that with 6.40, what we wanted to weld with 6.40 millimeter cap. This is extremely close. This is to program a welder with 500 pounds, 6.5 millimeter, 10 kiloampere, and 200 milliseconds. When we took 6 welds, average it, we got 5.56. So this is our program, okay? Once we go into auto mode, we make 6 welds, 2 coupons, and we result the average is 5.57. Compared with the manual weld programming, this thing, which is give us an average of 5.56, this is extremely close. We changed the weld cap from 6.5 millimeter to 7.5 millimeter. We expect to weld a bunch of welds which is 6.5 millimeter, 1 millimeter less than the weld cap area. We have to weld about 30 welds on the big sheets just to make the current adjusted to the right point, because the whole thing is designed to be able to adjust only 100 amps per weld. And the result is this 6 welds, average 6.51, which is 1 millimeter less than the 7.5 millimeter. The deviation is this value compared with this one. The largest deviation we have is 3.53%, larger than the average 6.51. This time we change the diameter of the cap. We have physically changed the cap to an 8.5 millimeter cap, and we make 6 welds. We expect the nugget size to be about 1 millimeter less than 8.5, so it's about 7.5. The average 6 welds resulted about 7.53, which is extremely close. This time the largest deviation is only minus 2.24%. On the production line, when your weld caps start growing larger and larger, the temperature, if you keep the same weld schedule, the temperature at the center of the nugget will become lower and lower, and this weld controller sends the temperature, so it will increase the current until the estimated diameter of the nugget go back to the right amount. For example, when you use a 6.5 millimeter weld cap to program this thing, and all of a sudden you change the weld cap to 7.5, then the weld size, the nugget size, will go to 6.5 millimeter. When I change the weld cap from 7.5 to 8.5, and this thing will keep on welding and predicting the diameter of the nugget until the prediction reaches 7.5 millimeter, then it will stay there. In real production line situation, you can't see that, because each time when you make a weld, the weld cap only increased a very small amount, so you couldn't even see it. Okay, so it look like this thing is keep on welding the good weld, no expulsion weld. This experiment was done March the 14th, 2014, on a Friday, and this is a group of 9 manual weld. In order to find out what the average is, so I can set the program estimated weld sizes. After I set the sizes, so I will go into the auto mode, capture the signal, and go into auto mode. This time I welded 9 welds and estimated from 5.51 all the way to 5.58. The real reading all the way 5.59 to 5.61. The largest deviation is only minus 1.46%. After I changed the weld cap from 6.5 millimeter to 7.5 millimeter, the estimated weld size should be around about 6.5 millimeter, and the real size should also be about 6.5 millimeter. The largest deviation is number 9. It's only 2.64% from the estimated. On September 15th, 2015, we used a 6.5 millimeter wildcat programmer to the low temperature well. And for sure, the nugget we got is 5.5 millimeter, which is 1 millimeter smaller than the wildcat. And every 2 coupons we peel, then we will put 50 welds on the big sheet of metal after we brush it with a brass wire brush. We keep on doing this that day, and we started out with 6.5 millimeter with 5.5 nugget size. But after the end of 622 watts, we're getting to 6.0 millimeter nugget size, which means the well cap have increased about half of a millimeter in 622 watts. The next day, we keep on going, and we welded 1,023 watts before we have the first expulsion wall. The expulsion wall, at that time, just before that, we measured the cap size, the 7.42 millimeter. Remember, we started with 6.5 millimeter. And after 50 watts or 100 watts, this well cap was center chipped. It healed itself. So the predicted well size gradually matched the real nugget size. At the end of the whole experiment, we total accumulated 1,238 watts, and the diameter of the well cap increased by 1 millimeter. And if you divide by 1 millimeter by 1,238 watts, so each well basically increased the diameter of the well cap less than 1 micrometer. Energy usage and energy saving. Very few people knows how much energy it takes to make a well. The most probable answer is I don't know, because there is no energy meter that can measure the energy intake at the tip wires. Most people just ignore the energy issue altogether. Actually, energy can be easily measured at the tip wires by integrating V times I, respect to time. With an intimate knowledge of energy, we can estimate the energy saving by using solid-state welds instead of expulsion weld. In physics, the P power is equal to voltage times current. That voltage is the instantaneous voltage, not the average. And the energy E is the integral from 0 to T V times I dt. the capital T is the weld time, or it's equal to 0 to T I square R dt. This is a simple calculation. We only consider the housing is a cylinder. Its diameter is 6.35, which is the cap diameter, and the thickness is 1.4, which is 0.7 plus 0.7, 1.4 millimeter. Area is 31.67 millimeter square. The volume is 0.0443 cubic centimeter. This calculates out to have a mass about 0.348 gram. Let's say the melting temperature of mild steel is 1500 C, ambient temperature 20 degrees C, so we have to raise this thing through 1480 degrees C. And the specific heat of mild steel is 0.49 joules per gram per degree C. So we calculate out to raise this little cylinder 1480 degrees C, it takes 252.4 joules. Energy used to heat this from 20 degrees C to 750 degrees C, which is the coalescent temperature, is only 124.5 joules. Okay? Latent heat of mild steel is 69.1 calorie per gram. We change it, it come out to be 289.25 joules per gram. So this calculator out to melt the whole nugget takes 100.7 joules. I add up the 100.7 to the 252.4 joules. I got 353.1. 353.1 divided by 124.5 give me 2.84. If we do this, just a cylinder, to melt this whole thing divided by the solid state weld 20 C to 750 C is about 2.84 times of the energy, which is pretty much as I can see, okay, which I predicted. And some people will argue that this is the ideal case, it never happened this way. You're absolutely right, because 3/4 to 80% of all the heat generated by the electric current is actually passed to the cooling water and the metal surrounding it. But at the same time, I don't have to melt the metal completely. So this is a good estimate. Another point which is very important is this 124.5 joules. To make a good weld, all the 0.7 plus 0.7, I normally need it around about 1200 joules of energy, which is 10 times of this 0 to 750 degrees C number. So I can estimate how much energy if I weld a nugget by using the 124.5 multiplied by 10. In July 2003, the Welding Research magazine, there's a paper, have a table, and this guy welded 3 weld and predicted 1 weld. And like the first weld is 0.75 plus 0.75 with a 6.35 millimeter cap, welding at 9.75 kiloampere. It's 150 millisecond and 500 pounds. He said he used 840,095 joules to create a 5.3 millimeter nugget. And the number 3 and number 2, it says he used 1.4 million joules. Prediction over here says use 1.2 million joules. Last one, it says use 1.1 million joules. At that time, I was welding exactly the same weld, and I was able to produce a 5.5 millimeter nugget with a 6.35 cap size, and I was welding between 1,000 joules and 1,500 joules. And so this guy must be wrong, because I was measuring. This is the first picture. The yellow color trace is the current. I was welding about 8.0 kiloampere, 300 pounds of force, and 6.35 millimeter weld cap. I set the energy I want to put in to 1,000 joules. So this thing welded about 100 milliseconds. And the output average for 2 coupons is 5.21 millimeter diameter. The second waveform, the top is still the current, the green color one is the voltage. And I'm still welding 300 pound 8 kiloampere. Except this time I adjust the energy to 1,500 joules. You can tell the weld time is longer. And out of the 2 coupons, 6 welds, the average is 5.41 millimeter. Since this is measured, so I can be sure I'm right. This is an energy meter I built to digitally integrate the voltage times current, DT. And this is, the first part of it is set about 200 milliseconds and about 12K. This is simulation, this is not on the machine. Okay? And then afterwards I changed the setting and read 37 something. Okay? So this thing is very, very useful. I use this meter to generate all those numbers that I will show you in later on of this video. This is the constant time variable current plot, energy plot. And we started with 9.0 kiloampere, and we found out the nugget is less than 5 millimeters, so we keep on going. until 13.5 kiloampere. These 3 welds are expulsion welds, so we will not count it, okay, in the system. This is a plot of current versus the energy with the time set at 200 milliseconds constant. And this is the current in kiloampere. And this is measured energy average per coupon of 3 watts. This is the measured average of the nugget size per coupon. And this is generated by a formula. This formula is found by using the Excel trendline option, and we can see this is pretty close, okay? This is the energy versus the current plot. Energy on the y-axis is in joules. Current is in kiloampere. And we notice right away from 9.5 kiloampere to 13.0 kiloampere, we all generated watts which is larger than 5 millimeter. Actually it's 5.21, larger than that. And which means the total weld load at 200 milliseconds is actually 13.0 minus 9.5. You have a total 3,500 amps of weld load. It is very, very wide. This is the formula or the equation found by the trendline method. This is the x-axis, which is the current in kiloampere, and the y is energy in joule. This experiment is constant current. We keep the current at 11 kiloampere. We started with 200 millisecond weld time to 25 to 50, 300, and we still keep on going. Until we reach 600 milliseconds. The last 2 coupons, we got nothing but expulsion weld, which is 550 milliseconds, 600 milliseconds. This column is the energy we use to make those welds. Expulsion weld is not a controllable weld, and the reading of its energy is actually not accurate at all. This is a table that shows the variable time and constant current plot. The current is 11 kiloampere. The energy over here are measured and the average of each coupon. And this is the diameter, average diameter. We can see over here we're basically in the low temperature weld region. Here we're more or less in the medium temperature region. And this one is after I plotted the curve, which very close to be a straight line. I used the trend line option on the Excel file I was able to find a formula, and that formula enabled me to calculate the energy usage as long as I'm working with 11 kiloampere, and whatever the time, I can more or less guessing the energy pretty close. This is the energy versus time plot while the current is constant. This is the energy in joule, and this x-axis is time in millisecond. You notice I did not plot any expulsion wall because I couldn't measure the expulsion wall anyway. And the blue line is the real line, the real curve. And after I plotted this thing, it looked like more or less a straight line, so I used the trend line option of the Excel file. I found a formula. I use this formula. I can more or less predict it as long as you're welding at about 330 amperes per square millimeter, or 11 kiloampere. In this case, I can more or less predict it, your energy usage, as long as I know what the weld time is. This is a spreadsheet I made to calculate the energy saving and the dollar saving. And first thing I want to remind you, making good weld consistently is priceless, regardless of what the energy saving is or not. This first line, I have to assume if I make a decent weld, solid state weld, how many joules I have to put in. And this is just a average value for all the welds, and this number actually I think is pretty low. Okay. The second one is what do you estimate the expulsion weld will use? How many times of energy expulsion weld will use over the solid state weld? Let's say it's 3. Then the expulsion weld will use 12,000 joules. The differences will be 8,000. Let's assume the system efficiency from the tip wire to the input meter is 25%. Okay, and so I take the 8, divide by 0.25, or multiply by 4. Okay, and that's the saving, 32,000 joules. Okay, and let's assume what? One machine is produce 7,500 welds per shift, and we have 2 shifts, and the working days per year is 250. So this is the number of welds we put out on this machine. And total saving is this number of welds multiplied by the 32,000. Okay? And then we assume this is a kilowatt hour saving. It's 33.3. Let's assume what? The electricity is only 7 cents per kilowatt hour. So each machine will save $2,333 per machine. This is more than enough to pay for this controller. The next part of it is number of welds per car. Let's assuming this is 4,000 welds per car. And this is the number of welds you can reduce by using the solid state weld. I assume it's 0%. I did not save anything. So I'm still making 4,000 welds. The energy saved by eliminating the welds is 0. And this is energy saved by welding solid state weld. Okay. Total energy saving. This is the kilowatt hour. Okay. And this with 7 cents per kilowatt hour come out to be $2.49 per car. But more importantly, each kilowatt hour equal to 0.524 pounds of CO2. So you're releasing much less CO2 into the air. Let's say a case we're using 5,000 joules, and this time we're only assuming the expulsion weld is 2.5 times the energy used by expulsion weld. So this is 12,500, okay, expulsion weld, okay, uses, and the energy saving per weld is 7,500. So that multiplied by 4 give me 30,000 joules of saving per weld. And then 7,500 welds per shift, 2 shifts, 250 working days in a year. And this is the kilowatt hour saving. This time I'm assuming you're using to 10 cents per kilowatt hour at your location. Then you're saving 3,125 cents per machine per year. That's more than enough to pay for the solid state weld controller. This is number of welds per car. This time I can reduce 10% of the welds. Then I save 500 welds. This is the real welds I'm putting on the car. And with this calculation, I'm saving $4.44 per weld. Okay? This is the same. You just change the assumption a little bit. You can find out how much you can save. Okay? Anyway, the most important thing I want to point out, it is making a good weld consistently is priceless. Okay. Advantages of welding solid state weld. Number 1, making quality welds consistently. Number 2, saving 50% to 65% energy, and at the same time making better weld. Number 3, expulsion-free weld controller / monitor inspects every weld. Number 4, reduce the number of redundant welds can save you more money. Number 5, you can use smaller inverters and transformers because only half to 1/3 of the energy goes through the system. Number 6, making the whole weld line safer and cleaner.